Hello, my name is Amelie Thomas. I am studying mechanical engineering at Louisiana State University. I will present here a description of my project, creating a soft robot testbed. At this time, I will present Phase 1 with some additional technical background and applications for the project, and then I will end with what Phase 2 will involve. When most people think of robots, they picture ones that are hard, heavy, or possibly humanoid. They have stiff movements and rigid members. Soft robots, on the other hand, are named so because, as shown in the picture on the right, they are made from more flexible materials. They are often modeled after great muscles found in nature, such as elephant trunks or octopus tentacles. The advantages of having these characteristics means that they have a more fluid range of motion and can grasp objects of varying size and shape. This makes them ideal for applications that require navigation of complex environments, such as surgical tools. However, with the increase in flexibility, there arises a challenge to maintain stability of position and grip. The objective of this project is to build a pressure-actuated robot and track its movements to gain understanding of the causes of instability during movement, and then to develop methods of improvement. The diagram shown here shows the three main systems that make up the testbed: the computer or controller, the pressure source, and the actuator. The computer will be the interface for the system, which should be able to handle manual input, but also programmable sequences for movement, and includes the pressure regulators. The pressure source comes from an external pressure source. In our case, it will be pressure from our lab building, and has a hand regulator to adjust it. The actuator itself consists of a configuration of three tubes encased in mesh sleeves, held together with spacer discs in regular intervals. And as you can see on the right, a final cap. When inflated, the tubing used for the muscles acts similar to a balloon. It will increase in diameter. The braided mesh surrounding it limits this increase in diameter and forces the tube to lengthen instead. When the three muscles are configured together, regulating the supplied pressure to each separately allows them to be shortened or lengthened, which curves the actuator and creates the shape of the arm. A controller or computer window will ask for the coordinates of the arm movement and then converts that to the corresponding voltage for each pressure regulator, which then adjusts each tube to the corresponding pressure. The system will need to map its input to the regulator's pressure output to produce the desired movement. This video shows another type of continuum robot that operates on the same principles, with the exception that it uses wire spools and tension instead of pressure for actuation. The motors driving it have a preset demo mode to perform the same routine with the push of a button. This capability could be beneficial for testing purposes to ensure a uniform movement across all trials. The next step will be to develop a tracking system for the robot's movement in order to get an accurate evaluation of its instability in certain positions. Initial research has found that an open source project called Chordata may be useful. It teaches how to build your own inexpensive motion capture system and provides software to run it. However, this may prove to be a complicated solution, and a simpler approach may be better suited to the project application. After the completion of Phase 1, the building of the testbed, the evaluation stages can begin by obtaining a monitoring system, measuring the movement of the robot, and finally finding suitable improvement solutions. If you would like to know more about continuum robots, these are some helpful resources which cover the types of continuum robots, how they achieve their curvature, and common testing. Thank you.